Okay, now let's take a look at how we can integrate from 0 to 1 x minus 1 over ln x dx. Unlike the previous one, this time we have the ln x in the denominator, and I can tell you guys, if you would like, try to come up with a power series for this. And I'll also tell you guys, good luck on that, alright? And just like what I mentioned in the previous video, we will be using a different advanced technique for this, right? So no power series in this one right here. So let's just think about what we can do. We know it would be so nice if we do not have the ln x, right? If we just have x minus 1, the world is so pretty, right? How can we somehow get rid of the ln x though? On the top, we have x minus 1. And is there any connection between x and the ln x? Well, let me just write a few things down on the side. Right, this is the intense thought process right here, so let me use blue. So we know that if I differentiate ln x, this will give me 1 over x, but you know, I want to get rid of the ln x. But what if I differentiate? Well, if I differentiate x, I just get 1, right? So it doesn't do me any good. How can I somehow produce an ln x though? How can I produce an ln? How about if I differentiate? Of course, if you have x to higher power, then of course you just get a power rule. But what if you have, let's say, 2 to the x, for example? Look, this is exponential function, and in fact I have a video recently for this, right? If you differentiate this, the function part repeats, which is 2 to the x, and you multiply by ln, right, of whatever the base is, which is a 2, like that. Hey, we come up with an ln. That's good. But here, I want to get rid of the ln x. Well, now, if you look at x as the base, then yes, just like earlier here, if 2 was the base, we multiply by ln 2 right here. If I can keep x as the base and somehow treat that as a constant, then we can produce an ln x. If you want to treat x as a constant, that means you have to have another variable. And the technical term for that is a parameter, right? So let me just put it down right here. So instead of saying d dx, let's say d dt, right? Just an example real quick. If I'm differentiating with respect to t, then if I have x for the base to the t's power like this is what? Now, this x will be just like the constant 2 that we had earlier, right? So as you know, this right here will give us x to the t's power first, and we multiply by ln x. And once again, you're looking at this x being like a constant, just like the 2, right? And the reason is because we are differentiating this with respect to t. And now that's a big progress right here for this idea, because if you look at this right here, on the top we have x minus 1, and technically I can write this as x to the first power. And now if I can define this to be a new variable, I want this, right, the exponent right here, to actually be my variable. So I can differentiate with respect to whatever that is. And then I can somehow produce the ln x. And maybe you guys have seen this technique in the past. This is called the Feynman's technique, right? But that's pretty much the thought process that why I want to do that. And this is how I will write it down for you guys. Okay, so here is the deal. I will just erase this. I'll keep these two differentiations on the board for now. So I would like to just say, I will let, right? Just say I want to create a new function. So I'll just say I, just like people say f of x or whatsoever, right? And traditionally, we use b, right? So let's say I of b, and I want to put the b right here, so that this will be my variable, right? I is a function of b, and this is going to be defined as the integral from 0 to 1, x to the b's power, and then minus 1 over ln x, like that, dx, right? Of course, over here I use t, but here I use b, doesn't matter, right? You can use t right here as well, right? That was just an example. Okay, now, if I define this right here, then you will see This original integral is the same as saying I of 1, isn't it? Because I want the b to be 1, so I can get the original integral. So that's the deal. And now, I will just do what we do. I is a function of b. Let's differentiate both sides with respect to b. So these kind of things will happen. Let's do that, right? So I will just do this in red. Why not? Differentiate this with respect to b. So db here, and then likewise db here. On the left-hand side, as you know, the derivative of I with respect to b, we can just write this down as I prime of b, okay? And on the right-hand side, when you differentiate with the integral right here, this is called the differentiation under the integral sign. This is the same as the following. You can look at the integral later, focus on the differentiation inside first. When you invite the differentiation inside of the integral, change that to a partial derivative, because inside here you have two different variables. So we will first do the partial, and I want to do this with respect to b first. And then we'll look at the function, which is x to the b's power minus 1 over ln x, right? So we do this first. At the end, we will integrate whatever that is with respect to x. And now, let's see what do we have right here. This is the integral from 0 to 1. Okay, in the b world, x is a constant. So let me just write down the 1 over ln x in the front first, okay? And now I'm differentiating with respect to b of the top. The derivative, right? The partial derivative with respect to b right here. The function part, which is x to the b's power, it repeats first. So let's put that down, x to the b's power. And then don't forget we multiply by ln of whatever the base was. The base was x, right? So we will have the ln x right here. And let me just make this right here in blue. This ln x, we got it just like that, right? You see, the base was x and the variable was t. Then we get x to the t times ln x. The base was x, the variable was b, so we get x to the b times ln x. And then this ln x in the denominator was considered to be a constant, so you put it in the front first. And then the partial derivative of -1 is of course 0, so this is what we have, right? And this is so wonderful because this and that cancel each other out. And of course, I will have to first close this integral by putting down the dx, and this and that, haha, nicely cancel out. So what you're saying is I prime of b is equal to that. And now I prime of b, we are just integrating, right? So this is just integrating. Let me just put this down better. X to the b's power in the x world. How do we do that? How do you integrate x to the third power in the x world? Don't be too crazy. This is just the power rule backwards. You add 1, right? And then you divide it by whatever the new exponent is, right? Because now the variable is the x. So come here, the variable is now x. B is just a number, just like the 3 here. So we can add 1 and then divide it by the new exponent, which is b plus 1. That's how we do integral right here, all right? Therefore, I prime of b is equal to x to the b plus 1 power over b plus 1. But, you know, we still have the lower limit and upper limit to consider. And keep in mind, we are still in the x world. These are in terms of x. X is equal to 0, x is equal to 1, all right? We plug in 1 and then plug in 0 and then subtract. So we see that I prime of b, this is equal to, once we are plugging 1 into x, I will have, and let me just show you guys all the work, 1 to the b plus 1 power over b plus 1, and then this is the first term, minus, plugging 0 into this x, so we have 0 to the b plus 1 power over b plus 1, like this, right? This is really nice, because this right here is just 0, right? So that's good. And 1 to the b plus 1 power, of course, that's just 1. So in another word, we will see that I prime of b, this is equal to just 1 over b plus 1, isn't it? And now, keep in mind, this is I prime of b. Our goal is to get I of 1. So, by looking at this, this is actually much better because to get I of b from here, we can just integrate both sides, right? We will integrate both sides with respect to b, right? Because remember, originally right here, we differentiated with respect to b first. Now we'll integrate both sides with respect to b, so put down the db on both sides. On the left-hand side, we will have just I of b, and I'll just put down the plus c, the constant on the right-hand side, all right? So this is equal to, when we integrate 1 over b plus 1 in the b world, we get ln, technically the absolute value, I'll put down absolute value, ln b plus 1 like this, and then we put down the plus constant c right here. Now, yes, I can plug in b is equal to 1 in here, but then I will get ln 1 plus 1 and then plus c. I don't know what c is. So before I plug in 1 into b, I should figure out what c is, alright? How can we do that though? Well, keep in mind, this was our original definition of I of b, right? I of b was the integral from 0 to 1 x to the b's power minus 1 over ln x dx. If I plug in 1, that's what I want, and I will have trouble. Why don't I plug in 0? Let's give that a try, right? By looking at this now, let b equal to 0, and on the left-hand side, we get I of 0, right? And this is something maybe we can figure out by putting the 0 right here. But let's look at what we have on the right-hand side. On the right-hand side, we will have ln 0 plus 1 and then plus c. This is also 0. So we're saying I of 0 is equal to c. But I of 0, based on the original definition here, this is the integral from 0 to 1 x to the 0's power, right? Because you plug in 0 into b. And then minus 1 over ln x dx, right? So this is equal to that. This right here, of course, ln 1, which is equal to 0. So this is equal to that. This is equal to c, okay? Now, what's this? We have to do this inside out, all right? And let me just erase this a little bit. We focus this inside out because the integrand here, when you have a solid 0 here for the b value, this is just x to the 0's power, which is 1, all right? 1 minus 1, which is 0, over ln x. All this inside turns out to be the integral from 0 to 1 of 0 and then dx, which is c. And you know, when you integrate, if the function is 0, you don't get any area. So it doesn't really matter what this is anymore. You can say that c has to be 0, right? So once again, you do this inside out, 1 minus 1, 0, that's pretty much game over. So you get 0. We are pretty much done. I of b is just pretty much this, right? Because here is 0. And let me write this down for you guys. Here we have I of b is just equal to ln absolute value of b plus 1, all right? And remember, our goal is to get I of 1. So now I can tell you I of 1, which is just going to be ln of 1 plus 1. You don't need absolute value at all because it's positive already, right? And let me just finish this up legitimately. I of 1 is that integral, so I'll put this down nicely for you guys. This looks extremely crazy, but the answer to this is pretty nice. It's just ln of 2. This right here is it. And now comment down below and let me know which one did you guys like better. Is it this one with Feynman's technique or the previous one where you had the ln x on the top and then somehow you end up with pi squared over 6? Let me know, but at the moment this is it. Subscribe to my channel. I will love you guys forever.